So in the last video, I talked about how we can measure a cell potential using a voltmeter. Again, I'll give you more examples of that later on. But each individual half reaction has its own cell potential. And so that's what we want to look at next is how do we actually determine those individual cell potentials for a particular half reaction? How can we kind of split them apart from each other? And it's great because then we've got all these puzzle pieces that we can try to put together and make a better battery, for example. Again, that's one of the ways that we can look at this. So first of all, as with gas parameters, when you talked about gas laws and that sort of thing, there were a certain set of standard conditions that we use to measure those gas values. We have a similar set of conditions here for electric potentials as well, although we use room temperature, not 0 degrees Celsius like we do with gases. So typically 25 degrees Celsius. When you're using a solution, again, under standard conditions, we have defined that as having a concentration of 1 mole per liter, or an activity of 1 mole. And then for gases, if a gas is involved, we maintain that gas at a pressure of 1 bar, which is close to 1 atmosphere of pressure, so or 760 torr, close to that. So those are the standard conditions. We're not going to do a whole lot at other temperatures or other pressures, but we will look at the effects that concentration can have a little bit later on. We'll look at some non-standard systems, but most of what we're going to examine throughout this this portion of the course is going to be under standard conditions. So that's again 1 molar concentration, 1 bar pressure, 25 degrees Celsius. The 1 molar concentration can be tricky because some of these substances that we try to use physically can't get to that high of a concentration. Some substances just simply that exceeds their solubility limit, to tie this back to solubility that we talked about earlier this semester. And so some systems, it's impossible to get it to that standard condition. Although, as we'll see, concentration ultimately has a rather minimal effect on the cell potential until your concentrations start getting really, really far away from that 1 molar concentration. I mean like factors of 1,000 or factors of 1,000,000, that's when we start to see some bigger deviations from standard cell potentials. So, the other thing we need to know then is how do we come up with the overall cell potential? Well, again, remember our electrochemical cell is made up of 2 parts. We have the anode part and the cathode part, the oxidation half reaction and the reduction half reaction. Each one of those has its own half potential. So each is a half reaction, each is a half a cell, each has a half reaction potential associated with that. So the standard electric potential for any redox reaction is simply the sum of, added together, the individual half reaction potentials. So you have an oxidation half reaction potential and a reduction half reaction potential. Just add those 2 half reaction potentials together. That will give you the overall cell potential. Now, some of you may have had this before, or instructors out there might be listening to this going, wait a minute, that's not what I learned. Now, I do it a little differently. So I talked about it in terms of the oxidation half reaction potential and the reduction half reaction potential. You may see another equation where it's the, the reduction minus the oxidation potentials. That technically is correct as well, but why are you subtracting them? Well, what you're using there are both reduction potentials. You're using the reduction potential of the oxidation half reaction, and we'll talk more about what we do to those a little bit later on. I'm talking about using the actual oxidation half reaction potential and the actual reduction half reaction potentials. And we just add those together. I think it's a little easier that way than this whole subtraction thing, but so check with your instructor how they do it. And, you know, they might be a little different. You'll hopefully get the same answer doing it my way versus their way. My way just kind of takes something else into account along the way there. So that's why I have it as just the sum of those potentials. So for my students, all you got to do is add your oxidation and reduction potentials together. You've got to make sure, though, that you've modified your oxidation potential value. So how do we do this? Well, we need a starting point. We need a reference. And so scientists ultimately settled on one particular reaction. It turns out this reaction was good at undergoing oxidation. It was also pretty good at undergoing reduction. In other words, it could go in either direction. So you could flip the equation around and it would still work pretty well. The other way to think about this particular reaction is it went along with whatever else you put in with it. So if you had a reaction that really liked to undergo reduction, this reaction would undergo oxidation. Or if you put it in with a reaction that really liked to undergo oxidation, this reaction could undergo reduction. So it just kind of goes along with, it's that friend you call up and you say, hey, you want to go to McDonald's for dinner? And they're like, yeah, sure. Or, you want to go to Taco Bell for dinner? Yeah, sure. I don't know why or wherever. Or, J. Alexander's. I don't know if you like fancier stuff. I don't get money from any of these. I don't get money from anything. Anyway, so to determine cell potentials, chemists use what's called the standard hydrogen electrode, SHE. So sometimes you'll see it just written as she. So she's a good electrode. Actually, it's a pain in the butt to work with this kind of electrode. But here's the one of the two possible half reactions for this. So it's hydrogen ion, or if you're using hydronium ion, you can do that as well. Depends on the textbook. Some textbooks use H+, others use H3O+. If you use H3O+, you just have some extra water on the product side for this. So 2H3O+ plus a couple of electrons, it makes hydrogen gas as one product, and then some water. So here, it's ultimately the hydrogen ion that is undergoing reduction. The H+ is gaining an electron to form elemental hydrogen with a 0 oxidation number in that case. So it's going from a +1 to a 0 for the oxidation number for that, gaining an electron per hydrogen atom. And so this reaction was ultimately assigned a cell potential of 0. Everything else was measured in reference to this. So this was just kind of the starting point, and then everything else is relative to this. But that's how we get those cell potentials. So that way, though, the cell potential of this half reaction wouldn't affect anything else because it's got a 0 value. So whatever you measured on your voltmeter then is basically the cell potential of that other half reaction, because this one was a 0 when you add the two together. So like I said a moment ago, the advantage to this equation is hydrogen gas is a good reducing agent, hydrogen ion is a good oxidizing agent. All right, if you remember those terms from Gen Chem 1. Or in other words, hydrogen ion is good at undergoing reduction, and hydrogen gas is good at undergoing oxidation. All right, it's good at reducing other things. Hydrogen ion is good at oxidizing other things. So again, they kind of go well together. So you can easily flip this entire equation around. You could have hydrogen gas plus H2O making H3O plus and a couple of electrons. And that too would have a cell potential of 0. You'll hear me say this throughout the next several videos. The only thing you'll ever have to do to a cell potential is change its sign. You will never multiply a cell potential by a number, like 2 or 3 or 4. All right? Even if you double the equation, you do not double the cell potential. I've got some slides on that as well. The only thing you'll ever do to a cell potential is change its sign. That's if you need to reverse it, if you need to flip that equation around. So just keep that in mind as we go through these slides. So this is a little diagram of a standard hydrogen electrode. Like I mentioned a few moments ago, it's a real pain to work with, mainly because of the hydrogen gas. It's flammable, so you can't have any sparks or flames around. You need to do this in a well-ventilated area. You need to maintain this 1 bar or 1 atmosphere of pressure. So you've got to actually kind of keep track of the pressure, and that's kind of a pain to do as well. I mean, if your lab's set up for it, fine, but to set one of these up on your own is really tricky. You've got to have 1 molar acid concentration there for your acid solution under standard conditions for that, and nice clean water as well for this. So essentially, you constantly bubble hydrogen gas down in. You also need a platinum electrode. Since hydrogen doesn't conduct electricity very well by itself, you need a way to tap into that electron flow. To do that, you need a platinum inert electrode. The platinum doesn't react with anything. It's just there as a conductive medium. So as the hydrogen gas bubbles over the platinum electrode, then you can get your transfer of electrons. If it's acting as the anode, electrons will come up this little wire and go over to your cathode. If it's acting as the cathode, electrons will come down through here to the platinum, where you get this reaction happening, and you'll actually get additional hydrogen gas being formed at the electrode here. And again, you can see the little salt bridge for that. And again, a very acidic solution down here, a 1 molar solution of acid, that's going to have a pH of 0. So this is a really acidic solution then for that. Right, so it's just kind of a pain to work with, lots of hazards with that and so on. So if we don't have to use that standard hydrogen electrode, we don't want to. But if you're measuring a cell potential for the first time, you need to have that as your electrode. So like I said, though, this reaction works well in both directions. As the reduction reaction, this is the same one I showed you just a moment ago. So the H3O plus gaining electrons to form hydrogen gas and some water, that's got a cell potential of 0, a standard cell. So again, there's that little 0 I was talking about next to the E that indicates it's under standard conditions. Or you can just flip the whole thing around. If you need an oxidation half reaction to go along with some reduction reaction, this reaction will work there as well. So hydrogen gas reacting with water, it forms hydronium ion and some electrons from that. So it's producing the electrons. Cell potential here, same 0 volts for that. So whichever way it needs to be used, it's got a 0 voltage for that. And again, it just goes along with whatever you need to put it with. All right, so it'll work as a cathode up here. It'll work as an anode in this case here. And like I said earlier, the only thing you'll ever need to do to a cell potential is change its sign. Of course, here, there is no sign. It's 0. It's not plus 0 or minus 0. It's just 0 in this case. But other half reactions, if you do the same thing that I did here, which is flip an equation around, then you'll change its sign. All right, you'll need to do that for every oxidation half reaction that you use. Those oxidation half reactions, where you're going to find these is in a table of reduction potentials. And all the reactions listed in that table are listed as reduction reactions with the electrons on the reactant side. If you need an oxidation half reaction, you're going to pull that equation out, flip it around, put the electrons on the product side. You've got to flip everything in that. When you do that, you'll change the sign on that cell potential. Again, we'll do some examples a little bit later on. So the way, again, as I said, I do things a little differently than the textbook does and some other things there. The way I treat this is to find your E0, your overall cell potential for a half reaction. It's simply the sum of the oxidation cell potential plus the reduction cell potential. Again, in those actual forms. Like I said, the textbook actually has the E reduction minus the E of oxidation, but they're just pulling those directly off of the table. Like for me, I change the sign on the oxidation number, then I plug it in here. Whereas there, in the other equation, some people would say it's simpler. You just take the E reduction minus the E oxidation from the reduction potential table. That's why it's different. All right, but real simple to find that. So as long as you know the two half reaction cell potentials, just add them together. Again, and that'll give you the overall cell potential. For galvanic systems, the spontaneous ones, your overall cell potential will be positive. For an electrolysis cell, those are the non-spontaneous ones, your overall cell potential will be negative. That's the only requirements for galvanic and electrolysis, is the overall cell potential being either positive or negative. All right. You can have, for a galvanic system, you can have one of these be positive and the other one be negative. The only requirement for it to be a galvanic system, spontaneous, is the total, the sum of the two has to be positive. All right? And same thing for electrolysis then. One can be positive, one can be negative. It doesn't matter which one. So it could be the oxidation, could be the reduction. As long as the overall cell potential for an electrolysis is going to be negative for that. So that's the only requirement. But you can have one positive, one negative. It's not just you're making both positive or you're making both negative for galvanic or electrolysis. It's the overall has to be positive or the overall has to be negative. So how do we do these? Well, we start out by pairing up other half reactions with that standard hydrogen electrode. For example, the zinc half reaction, the same one that I showed you in the very first one there. And zinc, when it's paired up with the standard hydrogen electrode, zinc acts as the anode. It's the one with the negative sign or the negative terminal, and the hydrogen electrode ends up as the positive terminal. So that tells us zinc is undergoing oxidation. The standard hydrogen electrode then must be undergoing reduction. And if we measure the overall cell potential using a voltmeter, so something like this little guy right here, this is a little Harbor Freight special. They're usually pretty cheap. You can get them for a couple of bucks there, and So you just turn that on. There's your cell potential reading. It's not hooked up to anything. But the black and the red leads, then you attach those to whatever your electrodes are, and then you've got to have your salt bridge in there as well. And you can see whether you get a positive or negative value for that. And so if you see a negative value, but you know it's a spontaneous, you've got your electrodes backwards. So we'll do a lab on that a little bit later on. But that's your voltmeter, so that's how you would tell this. So it says, for example, when a zinc cell is combined with a standard hydrogen electrode, the zinc electrode dissolves. So that's the first step, is just make some observations. What do you see happening over time? Is zinc being produced at the electrode, or is zinc dissolving? So in this case, they're saying zinc is dissolving. In that case, that's how we know it's being oxidized, because the zinc metal, 0, is going to form zinc ions. It's going off into solution. That's why you're losing that zinc metal there. And then hydrogen gas is produced at the standard hydrogen electrode. That's the reduction reaction for that. If you're taking H3O+, so you'd also see the hydronium ion concentration, your pH would start going up because you're getting less and less hydronium ion in that. So it's those kinds of observations that allow us to figure out what's oxidized, what's reduced, what's actually happening in these reactions. So measured with a voltmeter, we get a cell potential of 0.76 volts. So here's my zinc half reaction, the zinc metal forming zinc ion. Again, that's based on this statement up here, where the zinc electrode's dissolving. That means it's forming that zinc ion. We don't know what its cell potential is yet. The standard hydrogen electrode, like I said, that's got to be the reduction reaction, since it said it was producing hydrogen gas. So it's got to have the H2 on the product side. That means the H3O+ is reacting with some electrons. That one we've assigned that cell potential of 0. And then way down at the bottom here, if you can read that, then the overall reaction, measured with the voltmeter, has this cell potential of a positive 0.76 volts. So again, the sum of these two cell potentials, the unknown oxidation for zinc plus the known 0 value or assigned 0 value for the reduction half reaction, has to equal 0.76. That means if we solve this little equation, which is really easy to do because it just has the 0 there, that gives us an oxidation potential for zinc of a positive 0.76 volts. The really good news is, anytime you've got zinc as your half reaction, when it's being oxidized, it's going to have the same positive 0.76 volts under standard conditions. All right, what if your zinc ion is getting reduced to zinc metal? It's going to be that same 0.76 volts, it'll just be a negative 0.76 volts. Like I've said, the only thing you'll ever need to do to a cell potential is change its sign. All right, so you never multiply, even if you needed to double your zinc reaction, if you needed 4 electrons instead of 2 being transferred, it's still 0.76 volts for that. All right, so like I said, we use a voltmeter. Just showed you one there. Doesn't have to be as simple. You can use fancier ones, but again, the El Cheapo Harbor Freight ones seem to work pretty well. And so if you don't have a Harbor Freight near you, I'm sure you can buy more expensive ones at other hardware stores. Voltmeters are designed to give a positive reading when the positive terminal, the red lead of your voltmeter, is connected to the positive electrode. Right? And so if you're getting a negative symbol, again, a negative sign on your readout, just change the electrodes. That's going to help you figure out which one's being reduced. That'll be the red. Oh, you see that? Reduced, RED, red, RED. So that's an easy way to remember, as long as your voltmeter is set up properly. And the black lead is your negative lead then. That's going to be the oxidation. Remember we said for a galvanic system, the anode is negative. That's where oxidation occurs. Reduction is positive, and that's where the cathode is, or the cathode's positive reduction. So CPR, we talked about that earlier. So in the previous example, we get a positive reading with that red electrode on the cathode, on the hydrogen reaction, and the black lead would be on the zinc in that particular case. All right, zinc's not always going to be the anode. Zinc's not always going to be oxidation. It just depends on what it's paired up with. So if you pair that zinc system up with something that's even better at undergoing oxidation, then zinc's going to end up reduced as opposed to oxidized. All right, so like I said, for a galvanic cell, the anode is negative. That's where oxidation occurs. That'll be your black lead on your voltmeter. The cathode is positive. That's where reduction occurs. Like I said, you can remember that CPR relationship. All right. I've underlined the negative and positive and the galvanic because those are the only things that are true for the galvanic system. If you change it to electrolysis, the non-spontaneous system, this one becomes positive. this one becomes negative. You hook it up to the anode to the positive power source terminal, and you hook the cathode up to the negative power source terminal. We'll talk more about that later on, though. All right, so from there, we just then compare any of these reactions up. Now that we know what zinc is, we can get rid of the standard hydrogen electrode. We don't need that crazy setup anymore. We can start pairing the zinc electrode up with other ones. And again, make the same observation as zinc being oxidized or reduced. That's going to tell us positive 0.76 or negative 0.76, whether it's oxidized or reduced in each case. And figure out what it's paired up with. And measure the overall voltage, and then just subtract out 0.76 or add 0.76, depending upon what math you need to do. And you can find the cell potential of the other side of your half reaction, or the other half reaction as of your cell. So in this case, I connected this up with a fluorine cell, another really toxic chemical. Fluorine's not so much flammable, but it's really poisonous, and it's really, really difficult to work with. If you ever have some free time, look up the video of cesium and fluorine. Just do a YouTube search for cesium and fluorine. There's a really, really neat video showing the reaction between cesium metal and fluorine, and a very nice looking British guy that says fluorine all the time. So you'll see what I mean when you watch that video. Anyway, that's fluorine, really reactive stuff. And so since the fluorine electrode is shown as positive, here's the overall voltage, 3.63 volts. A lot more than that 0.76. So the zinc is only contributing 0.76 to that. The rest of it has to be from the fluorine in this reaction. So the zinc is being oxidized once again, because again, as it shows there, the zinc going to zinc 2+. And so positive 0.76 volts, again, for an oxidation. If it was reduction, if you flip this equation around, this would be a negative 0.76, but it's zinc being oxidized here. Fluorine is being reduced then. It's gaining the electrons to form fluoride ion, the same stuff you scrub on your teeth. So you don't scrub fluorine, elemental fluorine on your teeth because you would die. Although fluorine is not, or fluoride ion is not the greatest for you, but it just in small amounts it's good for your teeth. That's what we're trying to figure out. And then the overall cell potential is the 3.63 volts. So how do I find the reduction potential for fluorine? Just take the 3.63, we're going to subtract 0.76 volts from that. And so the fluorine half potential, the reduction of fluorine, is a positive 2.87 volts. So fluorine is great at undergoing reduction. All right. That also means it's really good at oxidizing other things. Fluorine is an excellent oxidizing agent because it's so good at getting itself reduced. All right. Another way to think of it is it loves to strip electrons away from other stuff. It's really, really good at that. And so it yanks those electrons away from zinc. There's a huge electric potential with that. All right, why don't we make batteries out of fluorine? Because it's a gas, it's really, really toxic, it's really, really reactive. And so if it ever broke open, you'd see flames and fire, and it would be bad. So even though it's got this really big voltage associated with it, it's very difficult to work with. So that gets into the engineering, chemical engineering aspect of this. And why don't we have cesium fluoride batteries? They would generate huge amounts of electrical energy. They're really, really dangerous to work with. All right. And so now we've got 3 standard potentials. We've got the zinc, we've got the fluorine, we've got the standard hydrogen. And you can just keep building them more and more and more until you get a big table of standard potentials. Generally, the table is shown as reduction. They basically, just to keep everything consistent, they list all of the half reactions in this table as reduction reactions. So they show some are going to have positive cell potentials, others are going to have negative cell potentials. They're all listed as reduction. Those ones with negative reduction potentials are better at undergoing oxidation. That's what you'll see for things like zinc or sodium or lithium. A lot of the metals that are easily oxidized have negative reduction potential tables. All right? They're more difficult to reduce. They're much more easily oxidized. And so here is a very tiny version of that table. I've got segments of that I'll show you in later videos coming up here. But in general, so these are all listed as reduction potentials. So all of them have the electrons on the reactant side. Right? When you go to build a cell, you need one reduction and one oxidation. They're both going to be found from this table. But what are you always going to have to do to the oxidation half reaction? The oxidation half reaction is going to be here, but the species being oxidized is going to be on the product side of this table. You're going to take that entire reaction out and flip it around. What do you have to do to the cell potential when you flip an equation around? When you convert it from reduction to oxidation, you're going to change the sign on that. That's going to be more so the case with these ones up at the top. And the way this particular table is laid out, it's got all these metal ions, lithium, sodium, magnesium, aluminum, zinc, all up at the top here with very large negative cell potentials. Lithium's a negative 3.04, or sodium is a negative 2.71. That's for the reduction of lithium ion to lithium metal. So what about the oxidation of lithium metal to lithium ion? Well, that's going to be a positive 0.304 volts. So as I've said, and this will be the last time on this video, the only thing you'll ever need to do to a cell potential is change its sign. When you flip the equation around and take it from reduction to oxidation, you're going to change the sign of that cell potential. Then once you've got your oxidation and your reduction half reaction potentials, add them together. That'll give you the overall cell potential for your reaction. All right, the trickiest part is finding what you need for that oxidation reaction on the product side, on the right-hand side of this. Once you find that, you're going to need to flip that around. We'll do some examples in the next video.